So a final talk will be given by Kelvin Risby, magnesium nanoparticle synthesis via aerosol routes.
Right, so hello, I'm Kelvin at the University of Cambridge. Is it not on? Okay. So I'm at the University of Cambridge working with Professor Adam Boyce. My presentation is on magnesium nanoparticle synthesis. I'll cover a bit of background motivation on this work, why we're looking at magnesium, what's interesting about it. I'll also cover a bit about the device we use to generate the aerosols. It's called the silver particle generator, actually, or SPG. And then I'll just share some results on the interesting shapes and sizes that we're able to achieve. Give a little bit of discussion about the nucleation and growth regimes as well. So why magnesium? Magnesium is actually a plasmonic material. And so this work originally came about in collaboration with a group at Cambridge led by Professor Emily Ringe, and their research interest is in plasmonic materials and their applications. And a plasmonic material is basically one that can manipulate light at the nanoscale. And it's able to do this because it can sustain collective oscillations of their electrons when they're exposed to an electric field. And so it acts to sort of enhance the electric field and concentrate energy at a molecular scale. And so this is really useful. It's got a wide range of applications from enhanced catalysis all the way through to like biomedicine, things like that. And fundamentally, it's a phenomenon that occurs at the surface of metal nanoparticles. And so the shape is really important. So if you look at the figure on the right there, taken from a study by Leary et al., they showed that you get a really strong local enhancement of the electromagnetic field at sharp corners of gold nanoparticles. And it's gold and silver that are typically used as plasmonic materials. However, they are rare earth metals, so they're a bit expensive, and that kind of limits their wide scale application and raises some concerns on sustainability. But magnesium, on the other hand, is very cheap. It's earth abundant. It's also biocompatible as well. And it's got a hexagonal close pack structure, which offers a bit more shape complexity compared to gold and silver, which are front center cubic. And so conventionally to make these nanoparticles, they're synthesized by colloidal techniques, which is a sort of liquid phase method. This is what our collaborating group also does, and they have some drawbacks in that their batch processes, they require multiple steps. And they also need the use of ligands and capping agents, which end up in organic contamination in the end product. That's kind of where this project fits in. We want to have a continuous flow aerosol technique to make magnesium nanoparticles and of high purity. So we want high throughput and high purity. So the silver particle generator, like I said, is what we're actually using to make magnesium aerosols. It's a device developed by Catalytic Instruments, and they're my industrial sponsor for my PhD as well. And essentially, it's a standardized vertical orientation tube furnace. So it gives you a bit more control and stability over a conventional horizontal tube furnace. And so on the right, all the way on the left-hand side is a actual image of what the tube assembly looks like. And what's going on is there's a tube that sits inside a slightly larger tube. That larger tube has a closed end, and that closed end acts as a reservoir for your precursor material. And that all sits inside a heater. And so you can introduce a flow in the annular space between the two tubes, and that flow can then pass over the evaporating material and carry vapor up through the central tube where it can cool, become supersaturated, and induce particle formation. Currently, it is marketed as a silver particle generator, but it's also possible to use it for a whole range of materials as well. And that's sort of part of the work I'm doing in my PhD, is exploring these materials. The requirement is that it has to have a sufficient vapor pressure, a sufficiently high vapor pressure at the operating temperatures that the SPG works at. Sort of that minimum vapor pressure line there. And obviously we're highlighting magnesium here. So the first thing we did was to use an SMPS to take some size distributions. And what we, sorry, I'll go too far. Okay. Yeah, and so what we see is a trend that we observe with all other materials as well, that when you increase increase the evaporating temperature, you also increase the particle size, and that's kind of what we expect. As at higher temperatures, you have higher evaporation rates. There's more mass flux coming off of the evaporating material, so you have larger particles. And then for plasmonics, that's an important thing because the optical response of particles is kind of dependent on their surface to volume ratio. So they study paper taken from RC advances where they showed that monodispersed silver particles will absorb and scatter different wavelengths of light. And then these are the solutions of those respective particles, and they show different colors. And that's also why we see like nice vivid colors in stained glass windows in churches. But what's really interesting is the shapes that we're able to achieve. So for silver in the SPG, what we tend to see is small spherical particles, and they aggregate to larger fractal structures like this figure on the left here. And that's kind of typical of all evaporation condensation techniques, like spark ablation, for example. With magnesium, however, I found that we're able to access a whole variety of really interesting faceted morphologies, and they have the potential to exhibit like nice, unique plasmonic response as well. And crucially, it doesn't really seem to occur with other materials and other metals that we've tried. And so we get things from sort of tetrahedral shapes to hexagonal plates and rod-like structures. What's particularly interesting is this shape on the end. We've been calling them bow ties or hourglass figures. This is a 3D sort of tomography reconstruction of that shape, of that same shape, that's done by a collaborating group. And what's really interesting here is that the sharp edges are sort of further enhanced by the concave prism faces of the hexagonal plates. And we don't tend to see this anywhere else. Like I haven't found it too often in literature elsewhere, so it's quite unique to this system. And I think these shapes can probably be explained by the nature of phase change. And what I mean by that is either the vapor to liquid or a vapor to solid nucleation and growth regime. So magnesium actually has a really high vapor pressure at its melting point compared to most metals. So in this plot comparing silver and magnesium, you can see that at the melting point, the gray dot, the vapor pressure is almost 3 orders of magnitude higher than that of silver. This is a log scale here. And so what that means practically is that there's a much larger operating range in the SPG where we can have particle formation going from vapor directly to a solid. For silver, that range is much smaller. That's and most of the particle formation occurs from vapor straight to liquid, which is the green portion of the silver curve above the melting point. And so for vapor liquid, particles nucleate as droplets, and they grow by vapor being attached and immediately incorporated into that particle. And the surface tension kind of stabilizes the growth, and you end up with something spherical. For vapor to solid, on the other hand, it's really different, and there's a lot of thermodynamics and kinetics at play, and that essentially dictate how vapor molecules are attached and how they're incorporated into the structure. So that, along with the growth conditions and the actual underlying crystal structure of the material, determines the shape that you get. And so by making a model in COMSOL to sort of represent the SPG, we can run a number of cases and operating conditions to try to target specific regions in the phase diagram. So these plots are temperature, the black curves, and nucleation rates in the magenta along the position of the SPG inner tube. And you can see for a condition of case 1 with conditions of high temperature and low flow rate, the critical nucleation point occurs somewhere in the tube where the temperature is above the melting point of magnesium. And so in the green region, we'd expect vapor to liquid nucleation. And when we take a sample and do some microscopy, that's pretty much what we see. We see these spherical or spheroidal particles. Conversely, for a case where we have much lower temperature and higher carrier gas flow rate, the nucleation threshold occurs, is surpassed at a point where the temperature is much lower than the melting point. And so we'd expect vapor to solid. And when we take a sample, we see that the particles exhibit very clear crystal habits. I've also taken samples for a range of other conditions to kind of isolate what the effective evaporating temperature is and carrier gas flow rate. So for the top row, it's all at a constant carrier gas flow rate of 2 liters per minute. We've increased the temperature, and we see at 700 degrees, we get these lovely sort of thin plates. And as we increase the temperature, they increase in size and thickness. And eventually, when we get to sort of 800 and beyond that, we lose some of the faceted structures and they become more polyhedral and spherical. Conversely, it's the opposite seems to be true when you increase the carrier gas flow rate. So that's kind of affects the effective temperature profile that the vapor and the particles experience. So for 800 degrees, with low flow rates, we see spherical particles as I've shown before. But then we see, as we increase the flow rate, a transition to more polyhedral shapes and eventually a return to really nice faceted plates. Finally, we looked at some of the particles under TEM PDS to look at their composition. We found they're quite pure. They tend to have a very small oxide layer on their surface, about 5 to 10 nanometers thick. But magnesium is actually quite reactive, and so this layer acts to sort of self-passivate the particles, and they can be stable in air for several days. So we can take these samples and we can give them off to our collaborating partners, and they can look at their plasmonic response. That's everything. So to conclude, magnesium particles are nice and they're a good alternative to traditional plasmonic materials. We can generate continuous high purity magnesium nanoparticles in the SPG, and we can also control their shape and size by tuning the evaporation temperature and carrier gas flow rate. And finally, we can achieve really interesting and unique morphologies. Thank you.
Thanks very much, Kelvin. Do we have any questions? Yep.
Thank you for nice presentation. I was wondering if you were talking about primary particle or aggregates when we look at the second temperature and flow rate.
These are primary particles. We find that they're sort of empirically, when we're looking at the samples there. Are you talking about this slide?
Yeah.
They tend to be, they don't tend to come out as aggregated as we see with other metals. Like these hexagonal plates, they're the primary particles that we see. They haven't sort of agglomerated and then sintered and coalesced, from our understanding.
So did you see any effect on agglomeration when you change the temperature and flow?
Not as prominent as we've seen with other metals. So it does happen. It actually tends to happen more at very low temperatures, where I guess there's not enough material to then form a large particle. But at high temperatures, because you sort of get beyond the melting point of magnesium quite quickly, they just sort of coalesce into spheres, and they solidify from there. They don't tend to aggregate so much after the SPG.
Thank you.
Mine is just putting a hand into it. Lots on the back. Go to the back first. We'll come to slum.
Rachel Miles, University of Bristol. So thank you, Kelvin, for that really interesting talk. I was going to ask, so you change your conditions and you see different morphologies forming. How uniform are those morphologies? Do you only get one shape for a different set of conditions, or is there some kind of dispersity to it?
There's definitely a trend, but yeah, we're sort of sampling polydispersed, and so we see a range of different sizes and shapes, but we see more of a trend of changing these conditions. Yeah, we've certainly seen the occurrence of interesting shapes like those bow tie ones in very specific instances, but it can be kind of hard to reproduce that and to just target shape. But it's more that we're able to target size with these parameters, and sort of we observe different shapes that we're not entirely sure how they form at this point.
What?
Well, Mr. Dadka, that was my follow-up question. I was just curious whether it's because you increase the gas flow rate, various things change, concentration goes down. But you said something about the temperature history changes as well, and also the residence time changes. So I was just wondering whether it was it's really interesting work.
Yeah, that's something that we want to look at more, because I think as you increase the carrier gas flow rate, they experience much sharper temperature drop, and so they experience much more extreme conditions of supersaturation. And it's in those regimes that really interesting things start to happen. You get growth instabilities, and there's a whole sort of topic on this, on how ice snowflakes form, and that's likely what's happening that results in some interesting shapes and certainly changes in shapes, but I think you need to try to focus a bit more on precise control and taking samples and looking at them.
Just a quick question, it's perhaps a question I should ask every one of you who presented, because you have 1 year of research left. You're near the end of year 3, so where are you going on the next year? Let's say you've got a fairly complete picture.
Well, I'm currently doing some more work on actually trying to modify the shapes downstream. So it seems to be very hard to control the actual shapes in the SPG. So downstream, I want to make use of like the critical growth processes to try to either evaporate them anisotropically or grow them into dendritic forms. So that would be the sort of final step for this project. To see if we can modify their qualities downstream under like diffusion limited conditions.
Thank you very much. Thank Kelvin again. Thank you all.